Hallo, hallo, hallo.
Fatto tipo biancaccio.
Buongiorno. The talk is 45 minutes.
Sì,
They're forced to come listen to me. Sorry. Yeah, see, I don't know why it's making those noises. It's making noises. Every time I move. Yeah. I don't honestly know.
Hey! Good morning. Thank you for attending this lecture, this seminar. The guest of today is Catherine Fitzsimmons. She's coming from the other side of the planet, and we are really honored to have her here, and I'm happy to have you here. 9 July, so I'm happy to see this room, this house of work here. And I think saying this, I will give to Ettore to introduce our guest.
So, hello everybody. Catherine, she's a researcher that works in arid and semi-arid environment. She's from Australia, but she worked for 15 years in Germany. She worked at Max Planck Institute and then University of Tübingen, where she was full professor in sedimentary geology. Now she moved back to Australia and she works as a physical geographer at the University of Monash in Melbourne. She did research worldwide. She worked in Tajikistan, in Morocco, remember
South Africa, gosh, Kazakhstan.
She just visited Campania, southern Italy. That's why she's here now. And we are doing some stuff. We've been in the field with Carlos here. In last week, we collected samples, and now Carlos will explain you why we are collecting samples from this region. So, Carlos, stay with you.
Grazie. Okay. So, in today's changing world, we really urgently need to understand the impact of an increasingly unpredictable future climate on our landscapes, the land on which we grow our food, our water supplies, our ecosystems. Conditions in marginal regions, like the edges of deserts and the Mediterranean regions, like Campania, for example, will become increasingly unstable. They're likely to become warmer, they're more susceptible to extended droughts, and this is going to make places like these difficult to support human populations. Now, since deserts and desert margins occupy about 50% of the world's land surface and host about 40% of the world's human population, this increasing instability is going to become a global concern for the future. Chi semina vento, raccoglie tempesta. He who sows the wind reaps the storm. Over the last centuries and increasingly over the last decades, humans have substantially transformed wild landscapes for our own use. The world's drylands and their margins are not immune to this. From the Sahel to the steppe, we've covered vast tracts with farmland and with pasture. But these landscapes are still governed by the natural processes of geomorphology and hydroclimate. What might happen in the future should these drylands cross over into instability? That's why I call this talk Chi semina vento, raccoglie tempesta. There is power in knowledge. As geoscientists, we can work to confront and hopefully mitigate that instability through our understanding of the Earth as a system, her processes, her changes through time, and the interactions between the spheres. As Earth scientists, we appreciate that sediments are one of the fundamental building blocks for these landscapes, and that we need to view these landscapes as part of an integrated system which intersects with the atmosphere, the hydrosphere, and the biosphere. Now, landscapes like aeolian dune fields, pictured here, they're beautiful and they're mesmerizing, but they also hold scientific value. Unconsolidated aeolian sediment deposits in drylands preserve massively important information about past conditions and the interactions between the atmosphere and the Earth's surface. So I'd like to go through and explain some of these pieces of information that we can extract with you today. It's no secret that we're living in times of accelerating global climatic change. In addition to acute crises like flash droughts, apocalyptic bushfires, I just read this morning that Marseille is on the edge of a giant bushfire, spectacular flooding, massive storms like we had in Napoli on Monday morning. Longer-term climatic or global observations of climate data also clearly illustrate this acceleration. So I'd like to show here the observed temperature anomalies at the surface for 2024. It was the hottest year ever recorded, versus a baseline from 1991 to 2020. And what we can see, I wanted to use the stick, but this is a bit difficult now, but is that the hotspots are mostly on land. On the bottom right, we can see the change in drought severity, again, according to a longer-term baseline. And where are the hotspots? Well, they're occurring on the desert margins. They're occurring in Australia, they're occurring in Central Asia, they're occurring in the Mediterranean. So our big question is, what might the future hold? Now, under accelerating global change, the overall dryland area is set to increase substantially by the end of this century. This is going to mean that some 2 billion people are going to find themselves under severe water stress by the end of the century under a 4-degree warming scenario. Now, these model-based visualizations and simulations help us to emphasize the importance of better understanding the interactions between the Earth's surface, the climate, and the hydrosphere. What sorts of landscape responses might we see in the future? Well, as Earth scientists, we know that in order to understand what future trajectories might hold, we need to understand the nature of past change. We need to know what sorts of landscapes might be possible in the future by looking into the past. Now, I'd like to show you here what the world looked like, what it looks like in the present day, and what it looked like in the last glacial maximum, so about 20,000 years ago. Now, in addition to the much lower sea levels and the vastly expanded ice sheets, the other thing that I'd like to draw your attention to is the vastly expanded deserts, in particular in Australia and in Central Asia. So essentially what that means is that the present day desert margins are effectively fossil deserts. So that begs the question, what are the thresholds for reactivating those fossil deserts into proper deserts in the future? So that leads me to my central research question. What can dryland sediments tell us about the interactions between the Earth's surface, the atmosphere, and the hydrosphere through time? Now, the key piece of evidence here is sediments. Here we've got some nice beach sand. So I'd like to structure my talk with 2 foci. So firstly, we're going to take a look at sediments through time, and we're going to work with luminescence dating, which is a dating tool which provides us with quantitative frameworks for rates of change and how landscapes have changed through time. The second part, we're going to take a look at sediments on the move, and particularly we're going to look at evidence for sediment transport and the provenance, so where the sediments are coming from and how that relates to atmospheric circulation. Now, in the end, hopefully, we're going to get a sedimentary perspective on hydroclimate and atmospheric circulation through time. As Ettore mentioned, I've worked in many parts of the world where we have dry and semi-arid environments. Today, mostly, I'm going to be talking about my work in Australia, because it's exotic, but it's also kind of cool. I'm also going to talk about some of my work in Central Asia, and I'll also try and touch on why I'm actually here in Campania with Ettore and Carlo. So, Australia is the driest inhabited continent on this planet, but it makes it a massive natural laboratory for exploring different aspects of dryland sedimentology. So to my first research focus, we're going to take a look at sediments through time. So we're going to look at chronological tools for change and rates of change. And specifically, I'm going to be working on or focusing on the Quaternary, and particularly the late Quaternary. Now, I'd like to introduce an important tool for this research question, luminescence dating. Now, this is an absolute dating technique. It's based on the physical properties of crystalline minerals, like quartz. Now, because they're natural, they're imperfect. So that means they contain defects within the crystal lattice. Now, within these defects, charge in the form of electrons gets stored. It's a little bit like a battery. Now, when we expose those mineral grains to sunlight, for example, through sedimentary transport, this results in the release of stored energy or stored charge, and we get a depletion of our battery, like on the left-hand side here. As those mineral grains get deposited and then buried, the ionizing radiation which is present in the surrounding sediments facilitates the trapping of charge again. Now, the rate at which that charge builds up is proportional to the amount of ionizing radiation present. Now we can measure this, and this is what we call the radiation dose rate. This is the bottom half of our age equation. Now, the amount of charge which is built up since burial is measured as recombined energy, which is released as photons of light. So here are some examples of quartz actually releasing photons of light. This is what we call luminescence. And we can actually measure that in the laboratory, and this is our radiation dose to sediment. So this is our age equation overall. Now, a few fun facts. We work with mineral grains like quartz and feldspar to some extent. We can work with single grains, and we can work with aliquots of grains. We can date sediments from around about 0 to 500,000 years in age, and we've got an uncertainty of about 5 to 10%. Now, when I first started in research with my PhD, I started working on linear dunes in the Australian arid core. Now, linear dunes, this is taken from an aeroplane, they're the most common dune type in Australia. They form roughly parallel to the resultant vector of the sand shifting winds. Now, in my PhD, among other things, I generated a temporal framework for aridity based on the phases of dune activity, which you can see up in the top part here. This is presented as a relative probability density function. So I then tried to match up the statistical age peaks for dune activity with flux of aeolian dust to the Tasman Sea, which is in between New Zealand and Australia, and also with the Antarctic ice dust. With limited success, partly because we've got kind of ambiguous and constantly moving sand dunes in Australia. So in my first postdoc, I then thought, okay, well, I'll move over onto the margins of the deserts. I'm hypothesizing here that the sediments on the edges of deserts might give us a less ambiguous picture of the desert expanding and contracting through time. Now, this required me to move into working on different kind of dune. This is called a lunette dune. So a lunette dune is a shape of a luna. It's a moon-shaped dune. It's transverse in morphology. So what that means is that this dune will form at a 90-degree angle to the sand shifting winds. Now, the other thing about this dune is that it sits on the edges of ephemeral lakes which are not always got water in them. So this is an example called Lake Mungo, and we're going to take a little look at this in more detail. Now, lunette dunes like this, they build up a vertical stratigraphic sequence, which gives us information about lake hydroclimate. Now, how does this work? Firstly, in a lake full stage, it's a little bit like a beach. So we have water, we have waves, the nice clean quartz grains wash up onto the beach, and then they blow up onto the sandy lunette dune. Now, I've done a lot of work on how humans have interacted with their past, with the environments over the past, so that's why I've got the human aspect as well, but we're not going to spend too much time on that. Then we get a phase where the lakes start drying out. Now, what then happens is the finer grained sediments on the lake floor then get exposed. Now, those finer grained sediments tend to then form aggregates which are sand-sized, but they're made out of clay. So what that means is that your dune then forms a mixture of both sand and clay aggregates. So we call that a saline clay or a paletal clay dune. Finally, sometimes these lakes completely cease to have any water in them at all, and you start to get soil development over the top. So basically what we have is the archive zone is actually in the lunette dune on the edge of the lake. That is what's giving us information about past lake filling and drying, not the lake floor itself. The reason being that it gets eroded. So I'll take you to a specific area now. This is known as the Willandra Lakes World Heritage Area. This is an important place because it's the site where there's the oldest known ritual burial on this planet. So we have ritual burials. We've got, it's been a really important place for archaeology over the past. Now, the thing about these Willandra lakes is that they don't have any water in them now, but they have filled and dried in the past, and they all have nice lunettes on the downwind side. The other thing about this is that you need to take a look at the scale of the catchment. This is 500 kilometres at the bottom. It's something like 800 kilometres from the headwaters into the lakes themselves. So when we're looking at lake hydrology records of the past, what we're effectively looking at is a huge catchment, which is bigger than Italy, I think. Now, it's a pretty beautiful and special and challenging place to work. And one of the reasons for that is because Europeans, when they arrived in the 1840s, they brought with them sheep and they brought with them rabbits, and that caused enormous amounts of erosion. And you can see here these badland kind of landscapes, which are spectacularly catastrophic amounts of erosion. But it does enable us to look at the stratigraphy, so it's useful in a sense. So how do we build up a framework for filling and drying in the lake? Well, this is an example from Lake Mungo, which is one of these Willandra lakes. And what I did was a number of stratigraphic transects. So here are 3 examples. And what we can see is different stratigraphic units, which build up a history of lake filling and drying over time. We can take a look at that in a little bit more detail. And what we find is the 11 different stratigraphic units. 5 units give us information about lake hydrology, and 6 units give us information about what happened in the lake after the inflow channel ceased to flow, and it actually evolved away, probably because of neotectonics, but that's another discussion. So in order to identify what the lake is actually doing at the time, we need to look at field observations, and then we also look at thin sections, so petrology. Now, if we look at the bigger picture, over the years that I've been working in this region, and other people too, we've developed a chronology which has hundreds of luminescence ages. And what I've done here is distill these into probability density functions, and I've basically divided this into 2 different states. Firstly, in the blue, we've got long-term permanent lake filling conditions, and in the green, we've got lake drying conditions, or conditions where we might have sort of seasonal inflow and then drying out. So on the left-hand side here, we've got the individual lake basins, and this is all of the lake basins distilled. Now, what we've got here is a record of lake filling and drying over the last 150,000 years. The best preserved chronology is actually from around about 60 to about 15,000 years ago, because 15,000 years ago is when we ceased to have fluvial inflow. And the other thing is that we've got lake full conditions which occur just before oscillating or lake drying conditions. So that fits nicely, right? So now that we have a long-term record of lake filling and drying, we want to understand the climate states which caused this to happen. So for this, we needed to work with some climate modelling. So what we did first was we tried to get an understanding of the catchment system hydrology. And this is a re-analysis of climate parameters for the present day. And we've got seasonal or monthly conditions for precipitation for the whole catchment, and then things like temperature and evaporation for the lakes themselves. Now, we're interested in the last 60,000 years. So what we've done here is we've worked with a data set which was published 5 years ago, which provides us with a time series. So from 60,000 to 0,000 years, paleoclimate parameters for that time period. So here we have the precipitation for the whole catchment, and then we have records of temperature. You can see things are getting warmer during the Holocene, during the last 10,000 years. Evaporation changes through time. So we did this in order to identify scenarios that are responsible for filling and drying our lakes by comparing that with our sedimentary record and our chronology. So what we then did with Markus Fischer, who is a postdoc in Potsdam, we undertook a water flux model. So we've got a lake cascade here. So we've got a number of lakes which fill, and then there's an overflow lake here. And we ran simulations for lake filling based on different volumes of annual water influx to the system. So on the left-hand side, we've got how the lakes might fill depending on how much water is coming into the system. So if we have 1 cubic kilometre of water coming into the system, this lake here does not fill. But once we have 2 cubic kilometres of water coming into the system, all of the lakes eventually fill over 200 months. It fills more quickly when we've got 4 cubic kilometres. So this little GIF is an animation of that threshold situation. Basically, we need 2 cubic kilometres of water per year in order to fill the lakes. Then what we did was we looked at that filling over 3 different kinds of conditions. So we looked at how the lakes might fill under present day seasonal conditions, then with annual spring flash flooding, and finally with 5-yearly flash flood events. Now, what we find is that it doesn't matter whether the rainfall is spaced out or whether it happens as a single flood, the lakes will still fill as long as there's a net average of 2 cubic kilometres per year. Okay, so how does that match to our sediment-based chronology of lake filling and drying? Well, what we find, so here is our lake filling and drying record. It looks a little different. The blue is the lake full events, and the green is the lake drying events. These blue bars are our lake full events, and the green bars are the lake drying events. Now, what we see is that before 25,000 years ago, we find that lake filling is driven by increased precipitation. So over this time, we've got peaks in precipitation occurring around about the same time that we've got lake filling. So that looks like, okay, we've got wetter conditions, the lakes are filling. Okay, that makes sense. If we then go to the last glacial maximum period, so from 25,000 to 15,000, we find that there's no increase in precipitation at this time. And in fact, there's really not a lot spectacular happening that might be driving those oscillating lake conditions. So we still have water moving into the lake and then evaporating, but what is actually causing it? Well, what we then need to do is think about the catchment itself. Now, the catchment itself, its headwaters, as we saw before, are 800 kilometres away. They're in the highlands of Australia. Now, we know that during the last glacial maximum, we had permanent snow there. So what we're hypothesizing is that the water that was coming into this system is because of seasonal snow melt. Now, this is something which is kind of, Europeans think this is normal, but in Australia, we don't get very much snow. So this is kind of a big deal. So it's effectively what this means from this story is that the lakes are filling at different times because of different climatic scenarios. And we wouldn't have known this without integrating our sedimentary record with our climate modelling and hydrologic modelling. So take home from this first part of the talk, it's really important to integrate the different environmental traces, and we need to look over landscape scales in dry lands. Luminescence works really well, and it's also really important to integrate the sedimentological data with things like climate modelling in order to better understand how the landscapes have changed through time. So I'll now move to the second focus of the talk and have a look at what sediment transport can tell us about interactions between the land surface and the atmosphere. Now, this links to the reason why I am here in Campania. The idea that we're trying to explore with Ettore is whether long-distance aeolian transport of dust has contributed to soils west of the Apennines, and if so, if we can uncover information about past atmospheric circulation patterns. Now, there are a range of tools which we explore in order to answer this kind of question. Now, I'm going to return briefly to the Willandra Lakes, and this is our lunette here. Now, what I found was walking over this landscape, and look at the scale, there's a lot of walking, is if we go back to that assumption that these lunette dunes are forming at a 90-degree angle to the wind vector, and what I found was that different stratigraphic units are actually thicker in different parts of the lunette. So what we see is that we've got a lake full unit, which is about 24,000 years old, which is thickest in the northern part. Now, that would suggest that the wind vector responsible for the transport is more like this, whereas the unit, which is deposited between 22 and 15,000 years, is thicker in the middle part. So that suggests that we've got more of this kind of trajectory, straight westerly. So that suggests that we've got some changes in atmospheric circulation through time. So now I'd like to take you to another kind of aeolian deposit, one which is maybe a little bit more similar to what we have in Campania. Now, for this, we're going to move west of Melbourne. And I don't know whether you guys are aware of this, but west of Melbourne is the third largest active volcanic field in the world. They're mostly scoria cones and little basalt cones. The last eruption was 5,000 years ago, so it is not extinct. So some years ago, I found myself working at a site called Spring Creek. This red material here is all the volcanic plains, and you can see that this site is sitting right in the middle of the basalt fields. It's a basalt catchment. Now, despite there being no quartz nearby, I observed clayey quartz silts dated to around about 29,000 years ago. And then above that, we start getting more quartz sands. So that made me wonder, well, where is this quartz coming from? We're at least 50 kilometres away from the nearest quartz outcrop. So my hypothesis was that that quartz must have been transported by wind. So what I then did was I worked with an atmospheric scientist, Sergei Gromov, who was based at the Max Planck Institute in Mainz, and we investigated past and present wind regimes using particle transport trajectories. So this is atmospheric modelling. And what we did was we looked at the likelihood of where the particles are going to be coming from in the present day and during the last glacial maximum. So the brighter colours are giving us an indication of where the winds are likely to be transporting sediments from. Now, it's quite small, I apologise. You can see it bigger in the paper, but here, basically, we've got more westerly transport to Spring Creek. So essentially what this means is that during the last glacial maximum, and presumably a little bit earlier as well, we had stronger westerly winds. Now, if you remember the geological map and our exposure of quartz sediments, they're over to the west. Now, what this suggests is that we've got quartz sand transport occurring during the last glacial maximum. That means that the last glacial maximum was likely to be dusty and very windy. That's the key message, but we wouldn't have known that without integrating the sedimentology and the atmospheric modelling. So I'd now like to move across to Central Asia. So far we've been looking at sand. Now, sand is a near surface, it's a saltated grain. And it's susceptible to things like interaction with topography, right? Now, if we start looking at dust is finer grained. It's potentially going to link much more closely to the larger scale atmospheric circulation. Now, if I talk about Central Asia, you may not be familiar with the geographic region. It's basically here. Now, this is a really sensitive climatic transition zone in the Northern Hemisphere. Basically, we have the monsoons coming up from the south, and we've got westerly winds which come across from the west, and then we also have northerly winds coming from the Siberian high in the wintertime. So if you think about this over longer time periods, over interglacial periods, for example, we had more intense monsoons. We had northerly migration of the intertropical convergence zone, that ITCZ, and that would have spilled over the monsoon into Central Asia. Whereas during glacial periods, we had more intense westerlies, the ITCZ had shifted further south, and we've got stronger, drier winds coming from the west. Now, we've been looking at aeolian sediment records from this region. We've got quite thick loess deposits. So this is wind-blown dust. Some of this is Karamaidan in Tajikistan, where we've been working. It's 150 metres thick dust deposit. And these provide us with excellent calendars of climate change in the past. So what we have is loess accumulation occurring during those drier, windier glacial phases, and less loess accumulation and overprinting by soil during the interglacial phases. So it builds a kind of layer cake where we can kind of read the climate. And what we've been doing is looking at in situ climate proxies, but also sediment sourcing, which gives us information about atmospheric circulation through time. So what I'd like to do is share some of the highlights of that sediment sourcing, that provenancing, which has a relevance to why I'm here in Campania. Now, we saw a moment ago that we can use atmospheric models to hypothesize where the wind is likely to be blowing from for a given grain size. So from this, we can start to hypothesize links between loess and dust deposits and atmospheric circulation. So here we've done a similar sort of thing. The brighter colours represent where we've got more wind blowing from. And the red dot here, this is the city of Almaty in southeastern Kazakhstan. And what we can see is that we've got a lot of local transport. We also have quite a lot of westerly winds, but we also have some seasonal transport coming from the north. Now, those models can give us an idea of how the dust is then linking to atmospheric circulation, but we need the sediments to give us the concrete data. So for this, we're going to turn to the idea of provenance. So the idea of using characteristics of source rocks to fingerprint our deposits. So this is going to give us a vector for sedimentary transport and climate circulation. So again, we've got this area in southeastern Kazakhstan. Here you can see it on the map. There's the Himalaya. This is the Tian Shan Mountains. And this is southeastern Kazakhstan. And we've got those three main wind directions. So what we're doing is we're working to develop a new method for provenance, which is using trapped charge in quartz. So if you remember right at the beginning of my talk, where I was talking about luminescence being based on the principle of trapped charge in defects within the crystal lattice. Now, some of those defects, they're called Frankel-Schottky pairs. They relate to different geometries in the molecular linkages of the quartz. Now, the formation of some of these defect types in the quartz, they're called E', seem to increase in intensity or frequency given an age of a rock. So if you have three potential rock sources of different ages, that's going to give you three different E' signals in the quartz signal. So the location of our source relative to the deposit then gives us a vector for the sedimentary transport and therefore the atmospheric circulation. So my former PhD student, Aditi Davish, is currently based in Lausanne in Switzerland, compared the E' characteristics of loess from Kazakhstan and from Tajikistan at two different ends of Central Asia. And what she did was she investigated the E' properties of the loess from those two regions, and we found that in the Kazakh loess, the E' is higher than in the Tajik loess. Now, this suggests that we've got older source rocks in Kazakhstan and younger source rocks in Tajikistan. And sure enough, what we know from the geology is that that is the case. So another little proof of concept looks at modern surface samples. And here we've got that region in southeastern Kazakhstan again, and we've got those northerly winds and westerly winds. We collected surface samples from different places. And here's the end loess area. And what we find is that we've got quite a lot of similarity in the local surface, and we've got a lot of similarity to the west and a little bit of similarity to the north. So this suggests that the models are backing up what we're observing in the sediments themselves based on this E' quartz provenance technique. Now, ultimately, what we want to do is see how this might have changed through time. And here we've got a study which looks at how that E' has changed before 10,000 years ago and after 10,000 years ago. And this suggests that we've got a change in source through time. So what we need to do then is go back to the potential source rocks and see what the vector was like before 10,000 years and after. Now, take-home messages from this, really important to integrate the earth science sedimentology with our climatic modeling, the information that we can get from dust trajectory analyses, and this helps us to better understand the long-distance, big atmospheric circulation processes. This new quartz-based provenance technique is a really exciting one, which I think we can potentially apply then to anywhere where quartz is moving around in the landscape. Okay, finally, I'd just like to give you an overview of why we're here, why I'm here in Campania working with Ettore and Carlo. Now, every spring, you'll be familiar with this, we observe the scirocco. So this carries dust from Sahara into Italy and west of the Apennines. But the thing is, though, is that nobody has actually looked to see whether we have dust in the sediments here. Now, nobody has also looked to see whether maybe that dust flux has changed through time or the direction of the wind has changed through time. One thing we do know is that a couple of studies from the modern dust deposits indicate that it is dominated by quartz. So this gives us potential to explore this quartz provenancing technique. But it also justifies why we're here in Campania, because if we've got quartz in our soils here, we don't have any quartz in the natural geology around Campania. We have limestones, we have pyroclastic deposits which have no quartz in them. This is a good place to start looking. Now, I have a little bit of experience with Campania exporting aeolian material. I have been working in the windblown dust deposits of Romania nearby the Black Sea coast. And of course, we're sitting right here in the Campi Flegrei. We know that this was the biggest eruption in Europe in 200,000 years. What I found in Romania was we had 1 meter of Campanian ignimbrite tephra deposited more than 1,000 kilometers away from the Campi Flegrei. The other cool thing is that we were able to, check it with the chemistry. It is definitely coming from the Campanian ignimbrite. There is a very abrupt contact with the tephra. And there are also sedimentary structures which show that, we've got grass which has been knocked over really quickly and we've got worms trying to escape. It's really quite cool. Well, having looked at that, I'm now interested to see whether we can identify dust coming from the Sahara into Campania. So that's what we've been doing for the last week, trying to find profiles where we might be able to identify some dust. So now, more than ever before, exploring geosciences from an integrated viewpoint is imperative, given the human pressures on the landscape and what the uncertain future climate might hold. So hopefully I've given you a small overview of how we can understand the role of aeolian sediments in understanding the climate system, past and present. And if we understand how those processes are acting on our land surface, we're hopefully better prepared to face the storm which is coming. So with that, I'd like to thank you very much for your attention. I'd also like to thank all of my collaborators from around the world and from my previous research groups. And I'd like to acknowledge the deep and continued connection held by the Australian Indigenous people to the country. There are humans who have been living in Australia for 65,000 years, longer than any modern humans in Europe. So I'd like to acknowledge that. Thank you.
Okay, so we have time for questions. First from the audience in the room, and then if there is anyone on the web connected in remote, just open your microphone and speak. But first, we start with the room. Any questions from the room, from the audience?
Bamboozled.
I will try the ask.
Okay.
Hi, nice to meet you.
Likewise.
Carlo Donatio, I'm the colleague of Ettore. Thank you for your interesting speech about dust and sails. We have some topics in common, thermal analysis and OSL. But we use this technique especially for transition environments like river mouth, lagoons, and fluvial areas. So, about the dust and rain sites, Campania region, so up to the last level, we have a lot of value bridges in the places. But no one studied the rain sites in this one.
No.
These sites are higher than the present Europe, and the direction is very different compared to the present day. So it's a good topic to start. Together with the dust,
Absolutely.
The question is, you use the brain sites, but not microscopic analysis of ports. It's not so common to combine the ports.
No, it's not.
For example, silicate and fiber-based are common. And we will study also the shape of this.
Yes, yes. So we do. We have. So I've only been in my new job in Australia for 6 months, but we have a machine now. It measures grain size, but at the same time, it also measures grain shape. And I think this is very, very important to look at aeolian materials because, you know, something which is very angular is unlikely to be long distance traveled. So it's an important part of the equation. Absolutely. Yes. Also. Yes. Yeah. Yeah. So that's part of it. Yeah. Hi.
I was just curious, how do you figure out what was the cloud cover?
Yeah, so I should caveat this by saying that this is not actually my work. This is a work that we're working with data from a paleoclimate model. So it's HADCLIM, I think. And it is like a climate reanalysis for different time slices at 1,000-year intervals. And it's based on a climate model which extends back into the past. So this is, cloud cover is part of it because climate modelers always include things like cloud cover. So this is an assumption. I mean, I don't think you can really say, you know, there was, for 1,000 years, there was 25% cloud cover. I don't think we can say that necessarily, but it has an impact on evaporation and relative humidity at the surface. So this is how the climate models actually work, is by integrating all of those different parts of the system based on modern day observations of how the climate works. And then they extend that back into the past once they add things like sea level change and ice volume change over the planet. So this is for a particular small pixel in a global climate circulation model. Does that make sense? Good.
So you're talking about someone compared the direction and you put it downwards.
Yep.
And then I think you're also talking about.
Correct.
Sorry, I don't know what fix that.
That's a really good question. So one of the hypotheses that we have about why do we get dunes like this, linear dunes, parallel to the wind, and why do we get dunes transverse, it appears to relate to sediment supply. So there is actually very little sediment in this area. And all of it gets blown up into these linear dunes. in regions where we have transverse dunes, so for example, along coasts, we have a lot more available sediment, and that enables transverse dunes, so dunes perpendicular to the wind, to form. The other thing is, of course, in this particular example, we've got transverse dunes which are forming like a shoreline along a lake. Yeah. So we also have these, am I correct in guessing you're from India? So in the Thar Desert, we have a lot of these as well. Yeah. You're welcome.
You have a question from the room or from the audience online? Just open your microphone if you wish to ask a question.
Nope.
We will check. Okay, one more question from Patrick.
Of course.
Have you never tried to calculate both the wind size of blades, the wind velocity?
Yes. Yes. And there's a lot of people who have been doing this with LUS. And there are some interpretations suggesting that you can do n-member modeling, right? So if you're looking at the whole grain size distribution, and then you might have an n-member which is 30 microns and one which is 4 microns. And then there is an inference that, you know, the 30 microns is something which is like a storm deposit, and the 4 microns is long distance deposit. So yes, we've done that. I personally don't like in over-interpreting that, because that can also relate to what is available, right? If you only have 4 micron material, you're not going to get an n-member, which is 30 microns. And you're not, even if you get storms, it's still going to be 4 microns. So I'm careful about, we have done it, but I'm careful about how we do it. Yeah, and the different modes. Yeah. You're welcome. Hmm? Yes. The Lut, it's a place I really want to go. Yardangs. Mm-hmm. Oh, really? You mean this one? Okay. Yeah. Well, I should also add that these sand dunes, they're maybe 8 meters high. And I think the Yardangs in the Lut Desert, they're like 100 meters high, right? Yeah. Those are, I think, more erosional products. And then on the edge of the desert, you get these dunes, right? Yeah. So it gets eroded from the Yardangs and then deposited on the edge of the desert as sand dunes. And you get also different morphologies of the dunes in the Lut because there is more sediment availability. Here we've got very little sediment, and what little sediment there is, it just builds up onto these tiny little things which are only 8 meters high. Yeah, but I'd love to go there one day, inshallah. Go for it. Mm-hmm. Romania. 1 meter. Yes. Correct. No, I mean, it was very clearly volcanic ash. When I first went there, I thought it was sand, just local sand. I couldn't understand why there would be sand there, but it looked like sand to me. And not knowing anything, and not knowing, I was new in Europe. I'd only been in Europe for 6 weeks. You know, I didn't even know about the Campanian ignimbrite. I went back and I tried to date it with luminescence. It doesn't work. It doesn't work because this is volcanic glass and it has no crystal structure to store charge. So luminescence isn't going to work. And that was when I started realizing, oh, there's this companion ignimbrite tephra. There was a colleague of mine who had, he had identified tephra in the Alt Valley in southern Romania. And he suggested that perhaps it was this tephra. And so that's when, so in the paper, you can see that the chemistry is there. So it's definitely a Plinian eruption, it's Y5 tephra. So yeah, that's how we could fix it. Yeah.
Okay, so thank you again.
Yeah.
Beautiful.
Piacere. Yeah, go back to class.